Thank you, Pallavi, and thank you all for turning up once again. I promise this is the last time I'm going to bore you for today. Uh, so this session is meant for summarizing some of the open problems that we have seen in the previous lectures, as well as discussing some other open problems that I did not discuss before. And I hope you'll find some of these problems interesting, maybe even work on them, and maybe even solve them. So here we go. Okay. So we have been talking a lot about fair division, right? Which is basically all about allocating resources fairly among people with preferences, right? And you have to take their preferences into account in terms of even defining what fair even means, and also developing algorithms for finding those fair solutions. Uh, and we have seen a bunch of resource types, right? We have seen goods, which are desirable, chores, which are undesirable, and mixed, which are complicated, right? Maybe desirable sometimes, undesirable other times, and so on. And as we saw in the last lecture, we can understand these resource types in terms of valuation classes. So monotone increasing valuations are corresponding to goods instances, monotone decreasing for chores, and mixed is complicated, but a nice subclass of mixed is the doubly monotone valuations. Okay, and doubly monotone has embedded in it goods and chores. Okay, the purely monotone setups. Okay, and this is the Venn diagram that we saw. Okay, so a subset of monotone is additive goods, a subset of monotone chores is additive chores, and likewise for mixed. Okay, so one of the results that I showed you was that for additive valuations over goods, an EF1 allocation can be computed in polynomial time, right? This was the round robin algorithm, right? So I don't know if you realize that, but this result was basically the focus mini lecture series, right? This is the focal result, and then we diverge from this result in various different directions. Right? So one of the directions that we generalized in was we took offense to this additive term, right? We said we want more general valuation classes, and we talked about monotone valuations and NV cycle elimination algorithm and so on, right? Another direction that we saw was to generalize the fairness notion, right? So EF1 was great, but we were more ambitious. We wanted EFX, and we talked a little bit about it. Another direction that we did not talk about so far, but we will in this lecture, is that of asking something called economic efficiency in addition to fairness. Okay, so it's not just enough to allocate resources fairly. You should do it in a way that you cannot improve upon in a certain sense, right? And yet another divergence that we saw was to go from goods to different resource types. Okay, so there are many different directions in which you can branch off from this single result. And as you will see, that this combinations of generalizations gives you a whole new set of open problems, right? So that's what we'll focus on in this lecture. Okay, so in the part one, let me just summarize what we saw for the goods case for all different sorts of valuations, right? So we discussed the EF1 notion, right? And for the goods case, we saw that for additive, it gives round robin, and for monotone, for additive, round robin gives EF1, and for monotone, NV cycle elimination does the job. Then we moved to chores, right? For chores, again, round robin worked well, and for monotone, a variant of NV cycle elimination gave us EF1. For mixed items, we observed that some combination of NV cycle and the top trading variant worked well for doubly monotone. But a nice open problem from previous discussion was how to get EF1 for general mixed instances. Right, so this is, I think, a very, very nice direction to start working on. Also, not very easy, but yeah, it will be very interesting to make any kind of progress on this one. Okay, so this was the first sort of generalization. In the second generalization, we talked about EFX, right? And the story here was not as satisfying, right? Even for additive goods, right? Even for 4 agents, we don't know whether an EFX allocation always exists or not, right? We don't have a proof, we don't have a counterexample, basically know nothing. Okay, and Same for monotone. So even for the monotone domain, we don't know whether EFX exists or like we don't have a counter example for monotone either, right? And because of these somewhat disappointing results, we resorted to this approach of discarding some of the items, right? And we got help from the charity-based notions, right? And there we were able to show some positive result, right? And EFX with charity allocation always existed. Okay, so this was sort of a saving grace for us for the case of goods. For chores, again, so just to remind ourselves what EFX means for chores, right? So in case of chores, remember you are removing the chore from your own bundle to offset the NV, right? And the difference with EF1 is that now we're asking for the removal of any chore to address the NV, right? EF1 just asks for some chore, EFX for every chore. Okay, that's the only sort of cosmetic difference. Here's an example. Um, and for chores, again, the picture is very discouraging. Okay, so we don't know anything about either existence or non-existence, right? Even for additive chores. So it's a wide open problem and very, very nice open problem to work on. Yes. Yeah, so for 2 agents, you can show the existence, but for 3 or more, we don't know. Right? Likewise, for arbitrary number of agents, but with identical preferences, you can again say something useful, but for non-identical, again, it's not clear what the situation is. Okay? Yes. So if we, yeah, so I think what you're suggesting is to add offsets, right? So given a chores instance, let's add large enough offset so that the matrix becomes positive. The trouble there is that an allocation that is NV-free for goods may no longer be NV-free for chores. Why? Because different people could get different number of items. Now, if that is the case, then the offset for the agent who's getting too many items is multiplied by that many items, right? So if different people get different number of items, you're offsetting their utilities by different amounts. So that makes it harder to transfer the results. Okay, even then, it's not clear how to do it. Yes, there are other more sophisticated reasons why it fails, but yes, it does not work. That's the short answer. Yeah, and I think this should be like somewhat clearer now, right? So chores are not just the negation of goods, right? Because we saw that NV cycle elimination does not, its natural adaptation does not work with chores, right? You can't just find and replace goods with chores and sources with sinks and hope that it gives you EF1. That does not happen, right? So you have to take into account the way fairness is defined for chores and then design algorithms accordingly. Okay. Okay, and here are some of the reasons why chores with EFX is a difficult problem. Again, this is sort of my opinion. Maybe your opinion differs from that. So I think the difficulty, the challenge of EFX has to do both with the design as well as the analysis of algorithms, right? On the design front, there are some very natural obstacles. One of them we have already seen, that if any algorithm that makes use of NV cycles, if it resolves arbitrarily chosen NV cycles, it might end up destroying the EFX property. In fact, it might even destroy the EF1 property. Right? So one has to be careful in choosing what kind of NV cycles to resolve. Right? Another potential difficulty, and this comes from the charity idea where we saw minimal NV subset and most NV agents, etc., is that it's not clear how to define a minimal NV subset for chores. Right? For goods, we drew this tree, right? And we went down the tree and we kept on removing items until none of the children nodes are NV. Right? But for chores, if you remove stuff, it becomes even more enviable. Right? The fewer chores, the more desirable the bundle is. Right? So it's not clear how to define these notions in the first place. So even if you say, okay, I want to find an EFX with charity for chores, if you're planning to use techniques like this, then you have to first define these constructs, and it's not immediately clear how to do that. At least it's not clear to me. Okay. And in terms of the analysis as well, there are some difficulties with chores that don't show up with goods. And that is that when you assign a chore to somebody, the sum of utilities of the agents drops, right? The social welfare drops. But when you resolve the NV cycle, the social welfare improves because people are becoming happier, right? So the NV cycle resolution steps and the item allocation steps, they are working in opposite directions, right? One of them improves the objective, the other of them makes the objective worse, right? And this thing did not happen with goods. So when you assign a good to somebody, the overall happiness increases. When you resolve an NV cycle, the overall happiness increases, right? So these two things are working together, and that's why you were able to make some potential arguments. But with chores, it's more difficult because you can go up and down, and it's not clear how to manage that. Okay, so these are just some difficulties which make it hard to use techniques from goods in the chores world directly. All right, right. So it's basically a can of worms. So what about mixed items, right? No. So here we actually know that EFX does not exist, even for additive instances. Okay. And the example is, well, okay, so first of all, how do you define EFX for mixed items? You should be able to eliminate NV by removing any good, and I say good in quotes because it should be good from the NVS agent's perspective, right? And any chore in the NVS agent's bundle, again, chore from the NVS agent's perspective. Okay, up to the removal of any such items, it should be NV free. And every good and every chore. For or, it would be EF1, right? Okay, so this is the notion. Okay, so here is an example where an EFX allocation does not exist, even for an additive mixed instance. Okay, I'm not going to prove to you why there is no EFX allocation in here. That's just that's a lightweight case analysis. But what I want you to notice is that, first of all, there's a small number of agents involved, right? Just 4 agents and 7 items. Okay, so it's a very restricted setting, very restricted counterexample. Another interesting thing is that every item is either a chore for all agents or a good for all agents, right? So there's some objectivity when it comes to the items. Like everyone is convinced that an item is either a good or a chore. It's not like an item is perceived as good by someone and as chore by someone else. Okay, so there is some consensus in that sense. Another interesting thing is that this instance is almost like a chores instance, except for this pesky good sitting in the middle. Right? So if I remove that, then it's a pure chores instance. Right? So just one good is giving us the non-existence of EFX. And another interesting thing is that the valuations are all powers of 2, as you can observe, right? And these are known as lexicographic preferences. So the way to read this is as follows, right? So let's look at the red agents, right? They have a very, very high negative value for C1, right? So they really, really don't want C1, right? In fact, any red agent would be happier, would prefer a bundle without C1 compared to any bundle with C1, regardless of what the other items are. Right? Even if all these negatives were turned into positives, right? Just because of the geometric nature of valuations, this is so bad, I really don't want any bundle containing C1. Right? That's how negatively bad it is. Right? Subject to that, any bundle without C2 is preferred over any bundle with C2. Right? By the same reasoning. And so on and so forth. And ultimately, any bundle with the good G is preferred over any bundle without the good G, of course, because it's a good. Right? So these are known as lexicographic preferences. These are a special subclass of additive preferences. And this counterexample is saying that even for that subclass, You can't have EFX. Okay. All right. Okay. So one nice open problem, I believe here, is that although an EFX allocation, we know it does not exist, but how do you check whether an EFX allocation exists or not? Right. Uh, is there a polynomial time algorithm for checking the existence, or is this is an NP hard problem? Like, what's going on? Okay. So I think this is a very nice question to work on. I don't have any algorithm for this problem. Okay, I mean, I don't have any interesting algorithm for this problem. Yeah, right. Okay. Okay, cool. Okay, so this is the picture for EFX, right? Okay, lots of open problems, like we barely understand anything here. Okay, so I want to move to a different generalization of this result, which is including some efficiency properties in addition to EF1. Okay, all right. So here's the motivation for this. So I mean, okay, so there is a trivial way of achieving perfect fairness, which is to not allocate anything, right? Even in that case, even I can solve the problem, right? So I think a bare minimum requirement that one could ask for is to allocate all the resources, right? This is known as completeness. But there are situations where even completeness is not a very satisfying assumption, and those are like this, right? So at the top, you're looking at an allocation involving 2 agents and 3 items, right? So A and C go to red, and B goes to blue. This is a complete allocation, right? Uh, but it's not a satisfactory allocation because you could come up with a different complete allocation that does not make anyone worse off and makes someone strictly better off. Right? That sounds like an obvious improvement that one could make. Right? So here the red agent has a value of 5, blue has a value of 2. In this case, red has a value of 5, but blue has a strictly higher value of 5. Right? So you're not hurting anyone, and someone is strictly better, so why wouldn't you do it? Right? So these kind of obvious improvements are known as Pareto improvements. Okay, so we would really like an allocation that is that does not admit such obvious improvements. Okay. So this notion is Pareto optimality. Informally, just says that to make someone better off, someone else should be made worse off, right? Um, here's a trivial example of a Pareto optimal allocation. You give everything to one agent, right? Now, if you have to make the blue agent better off, you necessarily have to take something away from the red agent, right? So you cannot improve blue without hurting red. Okay. And formally, we say that an allocation, well, not formally, but okay, pictorially, allocation B Pareto improves an allocation A if under B, everyone is at least as happy and someone is strictly happier. Okay, in terms of the value for their own bundles. Okay. And a Pareto optimal allocation is one that cannot be Pareto improved or obviously improved by any other allocation. Right? So any other allocation that makes some agent better off must necessarily make someone else worse off. So it's not an obvious improvement. Yeah. Okay. Easy to see that a Pareto optimal allocation always exists, right? You can just give everything to one agent. That's Pareto optimal, at least if the values are non-zero, right? So it's a notion that much like EF1 is guaranteed to exist and is efficiently computable, right? So now we have two notions, EF1 and Pareto optimality, both of which are guaranteed to exist and both of which are efficiently computable, right? And now a natural question is, well, are they mutually compatible, right? So does there exist an allocation which satisfies both EF1 and Pareto optimality at the same time? Right? So we know that these two notions exist individually, separately, but do they coexist? Right? Okay. What's your guess? Raise your hand. They are same. So wait, when you say same, you mean every Pareto optimal allocation is EF1? Because if you go back to the slide, this is Pareto optimal. So any EF1 is Pareto optimal? Here, this is Pareto. Do you think this is EF1? So there we go, right? So at least they're not the same properties, but is there an allocation at the intersection of these two sets, right? The EF1 set and the PO set, the Pareto optimal set. Any guesses? You think yes? Okay. Such as? Yeah, sure. Additive goods. Mm-hmm. Mm-hmm. Yeah, that's like a proof by example, right? Okay, but it's okay. Okay, all right, all right. Any other guesses? Good, coming up. Any other guesses? Okay, okay, we'll see, we'll see. Yes. Sorry, who's? Oh, yeah. Okay. Yes, whenever you do an NV cycle resolution, everyone becomes better off. So that's a Pareto improvement. Whether it gives you a Pareto optimal allocation is not clear. There may be other ways of making agents happier without making anyone worse off. We don't know. But NV cycle itself is a Pareto improvement. That's true. Okay, cool. So we can talk about EF1 plus PO as a notion in and of itself. Right? We can try to understand what is the landscape of results for these different types of resources, right? Just like we did for EF1 and EFX. Okay, so let's start with additive goods. Okay, cool. So to answer Vishwa's question, well, one of the algorithms that we saw for additive goods for EF1 was round robin. So it's reasonable to ask whether the round robin output is Pareto optimal or not. The answer is no. Okay, there are instances like this. Okay. Okay, so what else can we say? Any other algorithms for EF1? Lipton et al., the NV cycle elimination, right? Maybe that is Pareto optimal. That is also not Pareto optimal. So there are instances where that also fails Pareto optimality. And now we are basically out of ideas, right? We just have seen two algorithms for EF1. So one reason why this problem is kind of non-trivial is that EF1 and Pareto optimality are not natural companions, right? In the sense that if you start from an arbitrary EF1 allocation and you make a Pareto improvement on it, you may end up with something that is not EF1, right? So one might say, okay, EF1 always exists, right? Let me start with some EF1 allocation, and if it's not Pareto optimal, let me try to find a Pareto improvement and then keep on moving. This cannot go on forever, right? Because there's only finitely many allocations. So I'm bound to end up with an EF1 allocation. That does not work because of examples like this, right? So Pareto improvements may not preserve EF1 in general. This is not a proof, but it's just trying to say that they're not the best of friends. Okay, you can't get you can't preserve EF1 by making Pareto improvements. So if you want to come up with an allocation which is EF1 but not PO, that's easy. I'm not saying every allocation satisfies EF1 and PO. I'm asking whether there is some allocation which is EF1 and PO. So you can easily construct EF1 allocations which are not Pareto optimal. For example, round robin output. For example, NV cycle elimination output. Yeah. Exactly. Right. Okay. So that's where this gentleman comes to the rescue. That's John Nash, who you might have heard from game theory classes or from Hollywood movies, depending on your interests. So in 1950, John Nash proposed this objective function. It's called the Nash social welfare objective function. Not in the context of fair division. He was thinking about something called the bargaining problem, but I think it has relevance even in the context of fair division. So what is this? So A again is an allocation function, is an allocation, right? A1, A2, A3 are the bundles. V1 of A1 is value of agent 1 for its bundle. V2 of A2 is value of agent 2 for its bundle, and so on. So what this is doing, it's just multiplying the happiness levels or the utilities of the agents and taking the geometric mean. Yeah, so it's basically the geometric mean of utilities. That's what Nash social welfare is. Good? Okay. So with every allocation, you can associate a number, the Nash social welfare, right? And you can ask, okay, well, which is the allocation that maximizes this number? It makes sense to maximize this objective. Okay. So that's what we are going to call a Nash optimal allocation. I have an asterisk here, which is basically a corner case that, okay, if the optimal product is 0, how do you define it? Let's not bother about that. Okay, it's a technical condition. We can talk about it over the coffee break. Okay, but Nash optimal allocation is one that maximizes geometric mean. That's all we need to know. Okay. Interestingly, this turns out to be a very useful objective for us because some people showed a few years ago that any Nash optimal allocation satisfies both Pareto optimality and EF1 simultaneously. Okay. So I think the Pareto optimality part is easy to see, right? Because if A is not Pareto optimal, think of an allocation B that Pareto improves it, then every term is at least as large and someone is strictly larger. So that way you will be more than the optimal geometric mean. That's not possible. Right? So I think it's fairly easy to see why this is Pareto optimal. Not so obvious why this is EF1, but yeah, you can show it with like 10-minute proof. I'll be happy to do it later on, but maybe not now. Okay, but for now, just take it on faith from me that Nash optimal allocations have both of these nice properties. Okay, great. So I think existence is resolved, right? So this is for additive valuations, by the way. Okay. But now the computation question still remains. Right? So sure, you have shown me that an EF1 and PO allocation always exists, but how do you find one? Right? And there the news is not so great because at least maximizing the Nash social welfare, that's a very hard problem. Okay, that's hard to even approximate. So not only can you not optimize the geometric mean exactly, you cannot even optimize it approximately up to a certain constant factor. Okay, and this is true even for bounded valuations, right? So suppose all of the values in the valuation matrix are less than 100, even then this computational hardness result stands. Yes. Mm-hmm. Yes. Yeah, so there always exists some allocation which is maximizing geometric mean, right? Any such allocation is EF1 and PO. But if you want an efficient algorithm that maximizes Nash welfare, but it's unlikely. Or you're about to win $1 million, I don't know. Okay, all right, right? So Nash is hard, okay? But that still leaves the question, well, whether you can find an EF1 and PO allocation efficiently or not. Yes. What do you think? Right? So note that Nash was a sufficient condition for EF1 and PO, right? Nash implies EF1 and PO. And that sufficient condition is hard to compute, but it's not clear whether EF1 and PO is inherently a hard problem, right? And there is a sense in which you can show that it is not so hard, certainly not as hard as Nash, because there exists not a polynomial time, but a sort of polynomial time, a pseudo polynomial time algorithm for EF1 and PO. Okay. So what does pseudo polynomial mean? So note that the input to our problem was this valuation matrix, right? It's Vij, the value of agent I for object J. Now, the bit representation of that is that it takes log of Vij many bits to write that value. So any algorithm whose running time is polynomial in log of Vij, that's an honest to goodness polynomial time algorithm. The downside of this algorithm is that it's polynomial in Vij's, not log of Vij's. Okay, so that's why it's pseudo polynomial. Okay, but anyway, I mean, this is a different way of finding EF1 and PO. What is interesting about this result is that suppose the Vij's are all bounded. Okay, suppose all Vij's, all the numbers in your matrix are below 100. Okay, then this is a perfectly polynomial time algorithm, right? However, even in that setting, Nash continues to be hard, right? So for bounded valuations, this is a strictly different approach compared to Nash, as you can see from just the statements of the results, right? Yes. No, normalized, I mean, some valuations could be 2 to the n, right? So you never know. Yeah, so all values are, so that means the values are not growing with n or m, the number of agents or number of items. Okay. Okay, so I was hoping no one would ask me that. So Nash is hard even for 2 agents because of partition style reductions. So it's certainly NP hard. For I believe you might be able to say something for a small number of agents using maybe ILP approaches. I'm not so sure. I'll have to think about it. But yeah, I don't think there is an extensive parameterized study of Nash objective, to my knowledge. But it's probably the lack of my awareness more than our ignorance about the topic. So yeah, I may have to look it up. So yeah, good question. Okay, but okay, so another advantage of this result is that although it is not optimizing Nash welfare exactly, because that is hard, it's giving an approximation algorithm for Nash at the same time, right? So this algorithm here is a constant factor approximation algorithm for Nash, and interestingly, this is the best approximation algorithm we know for Nash, right? So 0.69 is the best we know. We don't know how to do 0.7 or better in polynomial time, and of course, doing better than say 0.99 is hard because of the APX hardness result. Okay, good. So coming back to our picture, we know that Nash helped us show that EF1 and PO always exist for additive, but whether you can find EF1 plus PO in polynomial time, even over additive domain, is I think a very nice problem to work on. Okay. What about monotone? Well, so there unfortunately exists an instance, even for a subclass of monotone called subadditive valuations, where no allocation is simultaneously EF1 and PO. So this existence that we saw for additive, it does not extend to monotone. Okay. Whether there is an EF1 plus PO for submodular is, to my knowledge, open. So submodular is something between additive and monotone. It's like that. Okay. So I think that's also an interesting problem to work. Okay. So what about chores or mixed items? Again, lots of lack of, sorry? Lots of sadness and lots of open results. So the sadness carries over from here because mixed is a generalization of that, right? And we don't know whether, even for additive chores, for example, an EF1 plus P allocation always exists. So again, one of the reasons for why it's challenging for chores is, first of all, because if you try to adapt Nash for chores, it's no longer going to work, right? Because you have negative numbers, right? So think of examples like this, where the values are -5, -1, and -5. Suppose you give A to red and B to blue. So the product of utilities is 25, right? So this is the algorithm that maximizes geometric mean, right? But this is not Pareto optimal, right? You could exchange their bundles and both agents would be happier. Both would be at -1. So the geometric mean worked very nicely for goods, but it does not work well for chores. Right? There are other issues as well. So if you have an odd number of agents, right, then they will have, then your product would be negative. So you'll have to take the 1 over nth root of the negative numbers, and then again, it's a mess. Yes. Chosen to what? So you're saying do a sign change? Yeah, so that would not work either, because again, any allocation that is NV free or EF1 or EFX for the sign changed instance may not satisfy the same properties for the original instance. You can construct examples to do that. Yeah, so I think one very nice takeaway from this lecture series should be that chores are not just a sign change from goods. They're really fundamentally somewhat different. Okay. And again, in terms of analysis as well, whenever you assign a chore, utilities of agents drop, right? But when you make Pareto improvements, for example, if you resolve NV cycles, the utilities increase. So again, these are conflicting objectives, and it's not clear how you can do potential arguments and such. Okay. All right. Okay. But that said, so there has been some recent progress on some restricted settings called the bi-value settings, right, where the valuation matrix has only 2 different numbers. There we can actually say that the F1 and PO allocation always exist. Sorry? So, sorry, I didn't get the question. I'm so sorry. Can I get rid of this somehow? So I think these are 2021 plus minus 1. Yeah, the slides are on my website, so if you want to look at it, you can always take a look at that. Yeah. Sorry about that. Okay, cool. All right. So this is the landscape of EF1 and PO. Okay, so we had some success here in terms of existence, but otherwise the picture is not very encouraging. Okay, so I just want to wrap up by saying that I talked about a very biased selection of topics, and there's a whole lot of other directions in fair division that people have looked at. One obviously is that I focused primarily on NV style notions, right? NV finishes up to 1 good, any good, and so on. But there's other notions. So we talked a little bit about proportionality in the context of cake cutting. You can also talk about it in the context of indivisible items and its approximations. There's something called maximum share, MMS. Again, look it up. Very nice notion. Something called equitability that I think came up in the discussion on cakes, but again, makes a lot of sense in the case of goods, and many, many others. Oh, Nimrod is here. Okay. There are also settings where you look at graphs, right? So what if agents are on a graph and you want to allocate items so that you don't envy your neighbors, right? So it's a limited form of envy freeness. You could also imagine a setting where the items are on a graph, right? And you want to allocate connected subgraphs to the agents, right? That's another very nice set of problems. Another strand in the literature is called the best of both worlds guarantees, which is roughly the following. So this reasons about fairness of randomized allocations, which is just a probability distribution over deterministic allocations, right? So any deterministic allocation, because you have discrete objects, right? There could be envy in it. Right? Imagine 2 agents and 1 item. No matter how you allocate it, there's got to be some envy, right? But a fairer way to allocate the item would be to toss a coin. 50% of the time give the item to one agent and 50% to the other agent, right? So such an allocation is ex post EF1, meaning after you toss the coin, right? It would be EF1, but it's an ex ante envy free allocation. It's envy free in expectation, right? So you would like to come up with a randomized allocation, a distribution over deterministic allocations, which is A, envy free in expectation, or ex ante envy free, and any of whose realizations is approximately envy free in the sense of being, say, EF1. Right? And we have some results on that in the last couple of years. What I did not touch upon at all is game theoretic aspects. Right? So I assumed agents are nice and truthful, but That may not be so in real world settings. So what if agents lie about their preferences, right? A standout result in this literature is that there is no EF1 algorithm which is truthful. Okay, so fairness and truthfulness are incompatible, unfortunately. Uh, yes, yes. So look at all the instances of the fair division problem. There's at least one instance where some agent could misreport its values and get a better outcome. So it's not saying that you can always lie and improve. There's just one bad instance somewhere out there. Okay, so it's not foolproof, so to say. Any algorithm which is EF1 must fail strategy proofness. Strategy proofness in the sense that any algorithm which is EF1 must, on some instance, incentivize some agent to lie about its preferences and improve. But that instance could be like just a one-off, right? So it's not saying that EF1 algorithms are usually many. It's just case result, right? Mm-hmm. Right. Yeah, absolutely. Versions of house allocation have been studied on social networks as well. For example, there's a social network of agents, and you're allocating houses, and you want to allocate them so as to say minimize envy, right? Envy among neighbors, either aggregate envy or minimize the maximum envy or whatever. So yes, it's a well-defined problem even in the house allocation setup. Mhm. So the notion of envy that makes sense in stable matching problems is called justified envy, right? So imagine, so think of this school and student matching example. I think that may have been mentioned, right? So if I'm a student who did not get his favorite school, right, and I see that another student got it, even though that student is below me in the school's ranking, then I have a justified reason to complain, right? Because I got an inferior school, I would have wanted to be in that better school, and that school also wants me back, right? So I have a justified envy towards the other student, and I think stability there is very natural. Yeah, so there is, yeah, I mean, yeah, definition wise there is I tend to mix up, like, so they're essentially the same concepts. It's just that one of them includes blocking pairs involving unmatched agents, but otherwise conceptually they are the same properties. Yeah, either currently matched agents or even an unmatched agent. So there's two kinds of blocking pairs. I always forget which is accounted for under justified envy and which is not, but okay, one of them is. um, Okay, and finally, there's also a lot of work on subsidizing agents to achieve fairness, right? Again, think of the two agent, one item example, right? You can't have envy freeness exactly, but what you could do is you could provide subsidy to the agent who did not get the item. You could offset its lack of fairness, right? And the questions there are, okay, given an allocation, how do you subsidize the agents so as to make it completely envy free? Or given an instance, come up with an allocation that minimizes the subsidy that you need to make it perfectly fair, right? And there's some work on those lines as well. Okay, there's a whole lot of literature. The slides are on my website. Take a look at it later. But just want to say that there's a whole lot of books, a whole lot of surveys, some very recent tutorials on the topic, right? A whole bunch of workshops have happened in recent years, and countless papers for you to read. So knock yourselves out. Okay, but let me stop here. Thank you.
Thanks, Rohit, for such a wonderful discussion. And
Thank
thanks
you.
for accepting our invitation. And
No, thank you. It was a pleasure. Oh, thank you. Thanks. Hello. Hello.
Hello. Hi Nimrod, are you there? Yeah, he's there.
Yes, yes. Can you hear me?
Yeah. Hi. Yeah.
Hi. Nice to see you again.
Yeah. Same here.
So, shall I take the floor?
Just a second.
Yeah, sure.
Yeah.
Hi.
Hi. So welcome to the second session on the open problems. So now we will discuss some open problems in voting theory domain. Yeah, we can.
So can you see me, hear me, and see the slides?
Yeah, we can.
Okay, and I have like half an hour? So shall I start, Pallavi, or I'm
Can
still
start.
waiting? Okay, thanks.
Thank-
Okay, yeah, so nice to see you again. Thanks for inviting me for the second time. So I want to speak about some research directions in the voting or preference aggregation parts of computational social choice. So I assembled some of them. It's of course slightly biased towards my own interest, but I try to make it as balanced as I can. Okay, so basically the way I wanted to speak about these open problems or research directions is is to show the difference or the gaps between the study of computational social choice, in particular preference aggregation and voting, and the real world. Because I think that there are some clear aspects in this gap between the real world and what social choice or preference aggregation can currently give us that makes these research directions more articulated. So basically, what I want to do is to list several gaps that I see from the between the scientific knowledge in social choice and what real communities need for the governance. Because basically, what computational social choice tries to achieve, at least from my view, and in particular in preference aggregation, is to allow to build tools for self-governance of communities and digital communities or non-digital communities, and to allow this community to make good decisions together. But there are still some gaps between what types of decisions and what settings in which those decisions are being made between the real world and what social choice can tell us. So here we will see, I think, 3 or 4 slides. All of them look the same. On the left, you see basically what I think is the current state of the art in social choice research. And on the right, I listed what I think is still missing from the research community or knowledge to be applicable to more real-world settings. So the first one is the following. So basically, Pallavi spoke about single winner elections and about multi-winner elections. I spoke yesterday about budgeting or participatory budgeting. So currently, social choice research can deal with communities that try to make several types of decisions, such as selecting a president that is captured by single winner elections or voting, and selecting a committee or parliament, which is captured by multi-winner elections, and certain kind of budgeting decisions, which is what I described yesterday. But in the real world, communities need to make much more decisions and much more involved types of decisions. And I think that what is really missing is a study of like a general aggregation platform, so general aggregation algorithms that can deal with different kinds of decisions simultaneously or in the same general way. So this is the first gap between social choice research and the real world that I could identify. The second one is the following. So if you recall, so my talk from yesterday and also Pallavi's talks, and basically this is the standard setting in social choice, that we basically assume that there is some community that is static, So the set of agents in the community do not change, and also the set of alternatives do not change, or candidates do not change. Basically, this is just a one-time decision. So there is a static community and a static setting of decision making, and then we want to find a good aggregation method or a good way to do this decision making process simultaneously. But actually, in the real world, community members can come and go. In some settings, like digital communities, members could almost freely come and go, and this happens quite in a dynamic fashion. And also, there are many decisions to be made. So there is still a gap between the static communities that social choice can offer how to deal with and how to develop aggregation methods for, and from the dynamic communities and dynamic decision-making process that is really happening in the real world. The third gap is that, as I said before, social choice basically deals with one-time decision-making, but in the real world, communities make a lot of decisions. And also, these are not just voting processes. So in the real world, really what happens in communities is that community members can propose some suggestion to change the status quo, for example, or to do some kind of a process of decision-making. And then there is some form of deliberation or discussion that happens. And then usually there is some voting. But all of these decision-making process is much more involved than simply making just preference aggregation or just voting, because it's a continuous and holistic process of proposing, voting, and deliberation interleave together. And still, this is not captured in the research in preference aggregation. And the last aspect that I wanted to speak about is basically the limited time and attention that voters have in participating in those decision-making processes that we try to develop for community decision-making. So basically, the standard model of social choice, as also I described yesterday, simply assumes that there is some community with some voters, and the voters will willingly and in a meaningful way will participate in the decision-making process by simply submitting the preferences in a good fashion. But actually, in the real world, if you also in national elections, but also in digital communities that try to self-govern themselves, you see many times that not all community members participate. And also, if even for some community members that do participate, they don't really participate in a meaningful way because they don't really spend the attention or the time that is required to really make up their mind and vote in a serious way, in a way. So therefore, there is still the need and this open problem of how to make decision-making processes and aggregation methods that somehow can be useful for settings in which the voters do not have enough time and attention, and it's not reasonable to assume that they will simply willingly participate in the decision-making process by submitting the preferences. And there is the need to deal with it, and also to try to incentivize, also with economic incentives, those agents to really participate and vote in a meaningful way and then to basically participate in the decision-making process in a better way. Okay, so these are the four aspects that I want to delve into slightly more in details next. And what I will do, basically, I will speak about each one of them a little bit, and then I will show some of the related work that and the studies that started to happen in these directions. But still, I think that these areas are largely opened from the research point of view. So the first one is general aggregation. As I said, computational social choice currently already offers some good ways and good aggregation methods that can allow community to make simple decisions, such as single winner or multi-winner or budgeting decisions, and also some other, but these are mainly the type of decisions that social choice can handle currently. But there are other types of decisions, and maybe like the first question is, what else do we want to aggregate, or what else should we develop aggregation methods to aggregate for? There are some answers, but I think that one possible answer is that it's also useful to have like a general framework that can handle any type of aggregation in a way, and to somehow deal with this idea, we try to offer this simple framework. Basically, we said, okay, so if you consider all of the types of decisions that maybe communities want to make, one simple way to view it is to simply say that there is some space, and this is in particular some metric space, and then all of the possibilities for the outcomes are elements in this metric space. And now how voting can be modeled in this framework. Basically, voters can specify, so each voter can specify their ideal point in this metric space, and then we want to come up with some general aggregation method that takes these. So if there are n voters, it takes n elements in the metric space and outputs one aggregated element of the metric space as the output of the election. And now basically we can take single winner election, multi-winner elections, participatory budgeting elections, and also other kind of types of decisions that the community may wish to make. And just if we want to use this framework, so the only thing that we have to do is basically to come up with a good metric space that will be relevant for this type of decision, and then we can run this general aggregation algorithm that runs on this metric space. So we try to do this for several things. And as I said before, what if we want to use it, basically what we need to do is to choose the metric space, to choose the elements of the metric space, and to choose the distance of the metric space, then to choose some kind of aggregation method that runs on metric spaces. For example, try to find the centroid, like the point in the metric space or the element in the metric space that minimizes the sum of distances from it. And then we have like a general aggregation method that can deal with any kind of decision. So in this paper, we show that this is somehow reasonable for single winner, multi-winner, and budgeting decisions. And then we try to think whether this is also a good idea for legislation. What I mean by legislation is, in a way, this is, I think, like the most general kind of aggregation, or the most involved aggregation type that we can hope for. Basically, think about a community of agents that want to decide not on a president and not on a committee or a budgeting decision, but they want to decide on a constitution. Or so basically, they want to decide on some text, on some string. And now, basically, so this is really a completely open field, and I think that the reason is that because text is much more involved than let's say sets of candidates for committee election or stuff like this. If we want to use this metric aggregation idea for legislation, it simply says that we can take all of the possible constitutions. If we want, say, to come up with a constitution for the community, all of them we can put in a metric space. So the elements of the metric space will be all of the text that we can think about. And then each voter basically provides to the system like her ideal constitution. So one text or string that describe her most preferred constitution or her most preferred text. And then we need to take those n texts and aggregate them into one text, which will be the constitution for the community. But this is really not clear how to do this. It's not even clear if this metric idea is even reasonable for it, but at least this provides some general way to try to achieve this goal of basically being able to aggregate more involved kind of decisions, which can culminate in basically aggregating text documents. Okay, so this is one open direction in preference aggregation. The second one is, as I said, social choice basically deals with static communities that make only one decision. So there is a set of agents, a set of alternatives or candidates or something like this, and we want to come up with output, so just one-time decision process. But there are, as I said before, in the real world, communities need to make many decisions, and also the community can change, so the setting is really dynamic. And so, yeah, so as I said, like the standard model is that there is some input and we want some aggregation method to output some winner, and that's it. And there are some ideas on how to basically generalize the model of social choice, or this standard model of social choice, to be able to deal with many decisions that come continuously in time. And indeed, there are a lot of this is like a table of each line, each row is a community, and you can see the number of decisions that they make in time, but you can think about any other type of community. And there are some ideas, and I think that the most promising idea is this idea of perpetual voting, a model that was proposed by Martin. And then we also did some work on this, and I can explain what is the general idea is simply to consider. So in the most simple case, you can do something as follow. So let's say that you have a community of 5 students, and they need to make a decision in each day of the week. Say they need to decide on which restaurant they want to go in each day. So one simple thing that you can do simply a one-time decision for each days independently. But this could cause some problems. In particular, say that there is a majority among the students. Let's say that 3 of them always like pizza and the other 2 always like hamburger. Then if we just do this one-time decision repeatedly, then maybe we will choose this pizza every day, and those minority of those 2 students will never get anything. So basically, they will be completely ignored for the rest of time. So this simple model of perpetual voting simply says, okay, so we have a set of voters. We have these 5 students in this example, but we don't have only one decision. We actually have several instances in time, or several steps or days or whatever. And for each one of them, we have an election. So we have, in this simple model, we have a global set of candidates, but the preference of voter can change from day to day. And we look at this combined. So basically, given such an input with 5 days, 5 students, and 3 candidates, we have this matrix of preferences. And we need to find a good aggregation method that takes this input now and outputs basically a vector of winners. So one winner for each day of the week. And now this makes the setting much more complicated, but there are some nice ideas on how to make this aggregation, how to make aggregation methods for this generalized model of perpetual voting. Okay, so this is another direction. A further direction, which is in a way even studied less than the last ones, is how to look at decision-making processes in a more holistic way, and to involve in the model not only the voting stage or the phase, but to look at it in a way which is closer to reality usually, in which community members can deliberate and talk and discuss, and then they vote, and maybe this happens interchangeably. So they speak a little bit, then they vote, then they speak a little bit again, and so on. For this, there are some works, but not too many. I put here a snapshot from quite famous deliberation and voting platform called Liquid Feedback. This is why this is in German, because it's a German initiative. But basically, you can see that, in these kind of platforms, really people deliberate and discuss, and then they vote. So really these things happen interchangeably, but still currently there are not really good models that try to capture this together. So here we try to do something. Basically, this is a very, very simplistic model of deliberation, but we just say that this is again operates on a metric space. So there are voters, that there is some metric space of the possibilities of the outcomes that are possible. And then each voter basically submits their ideal point in the metric space. Now you can simply aggregate those ideal points, those points in the metric space. But here we said, okay, people will deliberate and they will discuss. And as a result of these discussions, maybe there will be some coalitions. So what we try to formalize or to model is this aspect of coalition formation that happens due to deliberation. And we said basically that there could be some coalition that will form based on how close they are in the metric space, almost like clustering, but but in a slightly different way. And then we wanted to understand whether this dynamic process of clustering and moving from coalitions will converge to some consensus, or will it converge to some disagreement in the society based on the initial conditions of these points of the agents in the metric space, basically. But this is a very, very simplistic view at deliberation, because we don't really model how people deliberate and discuss. We just try to model what will be the outcome of deliberation. And in this work, the outcome of deliberation is in the joining and merging of and splitting of coalitions of agents that form around the ideal points in the metric space. Okay, and now the fourth and last aspect that really differentiate the current state of the art of aggregation methods and studies in social choice from the real world is the attention scarcity aspect. What I mean is that consider that you are some agent in a community that make many decisions in time. This means that for each decision you have to look at the proposal, or at the election, at the candidates and the alternatives, and you really have to spend some attention and some time, which costs you some non-negligible cognitive burden, to really make up your mind and vote according to what you really feel about this proposal. And some of the proposals are hard. Maybe a classical example now is the example of Brexit. So if you were living in the UK, then you really have to spend some time and effort to understand what is on stake, and whether you want Brexit or you don't want, and you want something else. And this costs some non-negligible cognitive burden. And in the real world, voters sometimes do not really have this time and do not really spend this attention. And this could really deteriorate the quality of the decision making eventually. Okay, so for this first, what is still missing is some mathematical model that tries to model this aspect of attention scarcity. So what you see here, I mean, you don't have to read the mathematics, but what you see here is basically one attempt to do this. And intuitively, it says that there is a setting with voters or agents, and with many proposals that come in time or in a static way, it doesn't really matter. And now for each voter and each proposal, let's say that these are just binary proposals. Still, for a voter to make up her mind about whether she liked the proposal, and then she would vote yes for the proposal, or whether she doesn't like the proposal, and then she will vote no. This could take some time. And then we said, okay, so let's say that you have M proposals, but each voter has a limited time, let's say 1 unit of time, and the voter shall split his attention or his time or her time among those M proposals. And now what is the effect of spending time on a proposal? It simply means that the voter will have higher probability in voting according to her true feeling, or true opinion. So then we said, okay, in this very simplistic probabilistic model, if a voter spends more time on a proposal, then there is a higher probability that the voter will vote according to her true feeling about the proposal. And now the problem is that we have the set of voters, we have the set of proposals, and we need to find the good algorithm that will split the community attention or community time in an adequate way, such that the probability that the aggregation of the votes that we really get, the votes that the voters will really submit to the ballot box, will be as close as possible to the true fate of the proposals, meaning we basically look at the real-world situation in which voters have limited time, and we try to approximate the result that the community will have. The decision that the community will have, we try to approximate it to be as close as possible to the result that the community will have, if they will have infinite time to devote to each of the proposals. This is the intuition behind this mathematical model. And given such a mathematical model, now we can really compare different solution approaches. And here I listed 3 solution approaches that are studied in social choice already, but some of them for different aspects. And I think that studying these solution approaches and advancing them, also in the context of trying to overcome this problem of attention scarcity of voters, this is really yet another open field in social choice. So let me try to explain what I mean by these solution approaches, and then I will stop. So the first one is sampling-based method. Simply, the idea is that when a proposal comes, instead of having a vote in which all of the community members participate in the vote, and then they have to read the proposal and spend some time. Basically, for each proposal that comes, the system sample a small subset of the population, and then this small subset will spend some attention on the proposal, and then they vote. So this is nice because voters do not have to spend time for proposals in which they were not selected to be in this sample subsets. But there is the risk that if the size of this subset is too small, then maybe the majority of the votes of those ad hoc committee members will be far away, or will be not accurate sample of the true population. So for this, there is the need to do this sampling in a good way. It's still not clear how to do this, but there are some ideas. So this is the first type of solution approaches to attention scarcity, basically to do sampling. The second is delegation-based methods. The most popular way is to do liquid democracy, in which basically voters can specify, instead of voting directly for each proposal they come, they can specify the name of another agent or another voter, and basically delegate the vote to that agent. And this delegation can happen or can be done in a transitive way, which basically result in some kind of ad hoc parliaments or committees, or dynamic power structure in the community, because several agents in the community will have a lot of subtrees of delegating voters that coming to them. So then there is still some knowledge lacking from basically how to do this delegation in the most useful way to improve the quality of decision making for the community. So this is yet another solution approach. And the last one that I wanted to mention is the crypto-economic method, or basically social choice with money. And the idea here is basically to use economic incentives to basically improve the quality of decision making of the community. One very simple way to do this is the following. So basically, when a proposal comes to the community, let's say this is a binary proposal. So if we would run a complete vote by the community members on this proposal, then maybe the proposal will pass or not. But the thing is that, we don't want to let everybody vote on it, because this is too time consuming. So what we can do, we can basically open a prediction market on this proposal and allow external agents to basically place bets on whether they think that the proposal will pass or not. And now if we engineer those markets to be of high quality, then now we can basically look at the bets of the external agents on those prediction markets. And for each proposal that the external bet says that this is going to pass, maybe we can really just pass the proposal without really having the community members to really have to look at the proposal. But this is depending, of course, if the markets are engineered in a correct way. Okay, so maybe this is enough from me talking. So I think that really advancing these research directions that could really help in bridging the gap between the real world of communities that have to really self-govern themselves in good quality. This could really bridge the gap between those and the current state of the art of computational social choice, in particular for voting theory or preference aggregation. Thanks.
Hello. Yeah.
Hello.